I want to start today by asking you to picture the most abundant element in the universe.
Right.
It is, I mean, it's literally everywhere. It powers the stars, it's in the water you drink, it's probably in the very molecules of the chair you are sitting in right now.
It is the fundamental building block of everything.
Exactly. The most common stuff in existence. And yet,
And yet, trying to catch it,
yeah,
cool it down to unimaginable temperatures, and then, shove it into a fuel tank to run a truck or an airplane.
yeah.
That is one of the most difficult engineering challenges humanity has ever decided to tackle. It's a real paradox.
We are, of course, talking about hydrogen, specifically today, liquid hydrogen, or LH2. And this is the paradox that we're going to spend our time on today. This isn't actually new technology, is it?
Not at all. Not in the slightest. I mean, if you look at the history of spaceflight, liquid hydrogen has been the heavy lifter, literally for over 6 decades.
6 decades. We're talking about the dawn of the space age.
We're talking about things like the Centaur upper stage in the 1960s. We're talking about the Saturn V rocket that took us to the moon.
The Apollo missions.
The Apollo missions, the giant external tank of the space shuttle. All of that was powered by liquid hydrogen and liquid oxygen. So we aren't reinventing the wheel here. We're reinventing the cart that the wheel goes on. We're trying to adapt it for a completely different purpose.
But now, and this is the key difference, we are trying to take that technology out of the vacuum of space, where costs are, astronomical and safety is managed by armies of NASA engineers.
Right, where cost plus is the name of the game.
And bring it down to the messy, bumpy, cost-conscious world of our highways and airports.
Precisely. It is a fundamental shift from a spare-no-expense government mission to a this needs to be profitable and safe for everyone commercial reality.
And that transition, I imagine, is where the problems start.
It's riddled with what engineers call unsettled issues, and that's putting it mildly.
To help us navigate those very issues, we are doing a deep dive today into a really fascinating document. It's the SAE Edge Research Report, and it's titled Decarbonizing Mobility with Liquid Hydrogen.
It's a great piece of work. The editor is Matthew E. Moran, and the development team is just a who's who from places like the National Renewable Energy Laboratory, major aerospace companies. These are the people who live and breathe this stuff every day.
And what I love about this report and why we chose it is that it doesn't just sell you the dream. It doesn't just show you a picture of a futuristic hydrogen plane.
No, it gets into the gritty, oily, freezing cold reality. It talks about the thermodynamics, the safety hazards, the economic valley of death that so many new technologies fall into. It gets into the sheer mind-bending difficulty of keeping something at minus 253 degrees Celsius.
Just 20 degrees above absolute zero.
Colder than the surface of Pluto. It's an extreme environment.
So, our mission today is to unpack this report. We're going to look at why we even need liquid hydrogen, how we make it, how we store it without it just boiling away into the atmosphere, and ultimately whether we can actually afford to build a future around it.
It's going to be a journey from the Launchpad to the loading dock.
All right, let's get started.
Okay, so to really understand why we are even having this conversation, why there's this massive global push, we have to look at the context. The report kicks off with some, well, genuinely sobering data.
And this is coming from the NOAA 2023 Global Climate Report?
Yes, and it doesn't pull any punches.
The numbers are stark. The report highlights that the global surface temperature has spiked 1.18 degrees Celsius above the 20th century average.
Which may not sound like a lot, but in climate terms, that is a massive, massive anomaly. It's a fever for the planet.
Yeah.
And when you look at the driver, the cause of that fever, it's carbon dioxide.
CO2 concentrations. They've hit 424 parts per million.
And to put that number in perspective for you, because it's hard to grasp, that is the highest level that our planet has seen in at least 800,000 years.
800,000 years. That's hard to even wrap your head around. That predates, well, us, Homo sapiens.
By a long shot. So the urgency is not really up for debate anymore. It's baked into the data.
And a huge chunk of that problem comes from the way we move things around.
It does. The transportation sector is a massive piece of the pie. We are talking about over 20% of global CO2 emissions. That's roughly 8 gigatons of CO2 every single year. So the mandate is crystal clear. We have to decarbonize mobility.
Which brings us to what the report calls the hydrogen proposition. Why hydrogen? I mean, we're seeing electric vehicles everywhere now. Why not just put bigger batteries in everything? Why complicate things with a gas that needs to be frozen to the temperature of deep space?
And that's a fair question. Batteries are fantastic for passenger cars, for delivery vans, for shorter ranges. They're getting better every year. But hydrogen offers something unique, especially for the heavy-duty stuff. When you use it, whether it's in a fuel cell to generate electricity or you're actually burning it in a combustion engine, the only byproduct is water, H2O.
No carbon, no soot, no particulates.
Nothing, just water vapor. It's a zero tailpipe emission solution. But the real reason, the absolute core reason we're looking at it for heavy mobility, for trucks, ships, and planes, comes down to one word: density.
Clean exhaust. That is the dream. But here, right at the start, is where we hit the first major hurdle that the report spends a lot of time on: the density dilemma.
This is the fundamental trade-off of hydrogen. It's a double-edged sword. And to get it, we have to distinguish between two types of density.
Okay, let's unpack this because it is absolutely central to the entire conversation. We've got gravimetric and volumetric. Gravimetric is all about weight, right?
Correct. That's energy per kilogram or energy per pound. On a weight basis, hydrogen is, it's a superhero. There's no other way to put it.
The numbers in the report are pretty staggering. It has nearly 3 times the energy of fossil fuels per kilogram.
Almost 3 times the energy of jet fuel. So, in theory, 1 kilogram of hydrogen gets you 3 times further than 1 kilogram of jet fuel. And for things that need to fly or move very heavy loads, being light is everything. It's amazing.
But you can feel the but coming.
There is a massive but, a huge one, and that is volumetric density.
Size.
Size, energy per liter or energy per gallon. Hydrogen is the lightest element, which means its molecules are tiny and they want to be really, really far apart from each other. At normal atmospheric pressure, it just takes up a huge amount of space.
So it's very light, but it's also very fluffy.
That's a great way to put it. It's fluffy. The report states it has less than 25% of the energy content per unit of volume compared to fossil fuels.
So let me get this straight. If you just had a tank of hydrogen gas at normal pressure, it would need to be the size of, what, a small blimp to power a truck for a day?
Essentially, yes. You would need tanks that are 4 times larger to get the same amount of energy as a standard tank of gasoline or diesel. And that simply does not work for a semi-truck or an airplane, where every cubic inch of space is money. You can't tow a giant balloon behind your delivery van.
Okay, so you have to squash it. You have to force those molecules closer together.
You have to squash it. And there are 2 main ways to do that. You can compress it into a gas at very, very high pressures. We're talking 700 bar, which is over 10,000 psi.
And that's what they do for hydrogen cars, right? Like the Toyota Mirai?
Exactly. For a passenger car, it works. You can fit those tanks out of the floor. But for heavy-duty mobility for the big stuff, even those compressed gas tanks are often too bulky and way too heavy.
Why are they so heavy?
Because to hold 10,000 psi safely, you need incredibly thick, strong tanks, usually made of carbon fiber wrapped around a metal liner. That adds a huge amount of weight, which eats into your payload and your efficiency. You end up carrying the tank instead of the cargo.
Which leads us, finally, to the star of today's show: liquid hydrogen.
Right. If you want to get the best possible density to pack the most energy into the smallest and lightest possible space, you have to turn it from a gas into a liquid.
But hydrogen is stubborn.
It's incredibly stubborn. It does not want to become a liquid. It doesn't liquefy until you get it all the way down to minus 253 degrees Celsius.
Again, just 20 degrees above absolute zero. That's colder than Pluto. It's an environment that basically doesn't exist naturally anywhere on Earth.
It is an extreme, extreme environment. But if you can achieve that, if you can tame it, you solve the density problem enough to make hydrogen viable for the big applications, for the long-haul trucks, for the massive container ships, and for airplanes.
You can finally fit enough energy into a reasonably sized tank to get the range and the power you need.
That's the goal. That's the prize.
So we know why we need it. But the next big question the report tackles is, well, where does it come from? Because you can't just dig a hole and find a pool of liquid hydrogen.
No, you're right. Hydrogen is what we call an energy carrier, not an energy source. You have to use energy to make it. And the report outlines a few main pathways, or feedstocks, as they're called.
The most common one today, the incumbent, is steam methane reforming, or SMR.
That sounds very industrial.
It is. It's the legacy method. Accounts for something like 95% of all hydrogen produced today. You take natural gas, which is mostly methane, CH4, and you hit it with high-pressure steam and heat. It basically strips the hydrogen atoms off the carbon atom.
But, and this is a really big catch, it produces carbon dioxide as a byproduct.
So if we're doing this to save the climate, that seems wildly counterproductive. If we were just shifting the emissions from the truck's tailpipe to the refinery, have we actually solved anything at all?
It is counterproductive. It's what's known as gray hydrogen. It's actually worse for the climate in some ways than just burning the natural gas directly.
So what's the fix?
The fix is something called CCUS carbon capture, utilization, and storage. If you can bolt on another process that captures that CO2 before it gets into the atmosphere,
Hmm.
and then you either bury it deep underground or use it for something else.
Then you get what they call blue hydrogen.
Exactly. You get blue hydrogen.
Yeah.
It's a much cleaner option, but the report is quick to note there are still risks there, specifically with methane leaks in the natural gas supply chain. Methane is a potent greenhouse gas itself, much more so than CO2 in the short term.
So it's better, but it's not perfect.
Not perfect. It's a bridge.
Okay, so that's the fossil fuel route. What about the green route, the one everyone talks about, electrolysis?
This is the one that gets everyone excited. The concept is beautifully simple. You take water, H2O, and you zap it with electricity.
You run a current through it.
And it splits the molecule into its component parts, hydrogen and oxygen. If that electricity comes from a clean source, like a wind turbine or a solar panel,
Then the whole process is zero emission. You get green hydrogen, the holy grail.
it is. It's the ultimate goal. But, as with everything we're discussing, the report points out a major practical problem. The grid issue.
Intermittency.
Exactly. The sun doesn't always shine, and the wind doesn't always blow. These massive, multi-million-dollar electrolyzer plants need to run 247 to be economical. You can't just turn them off when it gets cloudy.
So connecting them to the main grid, which has a mix of energy sources, can be tricky.
They're very tricky. The report suggests that a better model might be dedicated microgrids.
What does that mean?
Imagine a massive new wind farm built out in the desert, and right next to it, a brand new hydrogen production plant. The wind farm is connected directly to the hydrogen plant, completely bypassing the main public grid.
So it's a closed system.
It's a closed system. This avoids congestion on the main power lines and ensures a dedicated 100% renewable supply for making that green hydrogen.
Now, there was one other source mentioned in the report that I found absolutely fascinating because I really hadn't heard much about it. Geologic hydrogen.
Yes. This is a really cool emerging field. It's sometimes called white or gold hydrogen. The idea is that there are pockets of naturally occurring hydrogen gas deep underground.
So it's already there. We don't have to make it.
In some places, yes. It's often created by natural geologic processes, like water reacting with iron-rich rock formations. And the idea is that you could drill for it, almost like you drill for natural gas.
That would be a complete game changer. No electricity needed for electrolysis, no carbon capture needed for SMR, just a drill.
It would be revolutionary. The report treats it as a fascinating emerging option rather than a guaranteed solution right now. We're still in the early exploration phase, trying to figure out how much is down there and if we can get it out economically. But it's definitely an area to watch.
Okay, so let's assume we've got our hydrogen gas one way or another. Now comes the really hard part. We have to freeze it. The report calls this the liquefaction bottleneck.
This is where physics starts to charge a very steep toll. To get a gas from room temperature all the way down to negative 253 Celsius, you have to use a process. The report mentions the Claude cycle.
What is that in simple terms?
It's a multi-stage refrigeration process. You compress the hydrogen gas, which makes it hot. Then you run it through heat exchangers to cool it down. Then you expand it rapidly through a valve or a turbine.
Like how a can of compressed air gets freezing cold when you spray it.
Precisely that principle, just on a massive industrial scale and repeated over and over in stages to get colder and colder. But this process is incredibly energy hungry. And the report highlights a key metric here called specific energy consumption, or SEC.
And the numbers here are brutal. I remember reading this section and just thinking, is this even worth it?
It's a very valid question. Current real-world liquefaction plants burn about 10 to 15 kilowatt hours of electricity just to liquefy 1 single kilogram of hydrogen.
Okay, put that 10 to 15 kilowatt hour number in context for us. What does that actually mean?
A kilogram of hydrogen itself contains about 33 kilowatt hours of usable energy. So you were spending 10 to 15 kilowatt hours just to get it cold.
Wow.
That means you are losing roughly 35% to 45% of the energy value of the hydrogen itself before it's even left the plant.
That's staggering. It's like filling up your car, but you have to pour a third of the gas on the ground just to get the nozzle to work.
That's the energy penalty we are paying right now with today's technology. It's a massive efficiency loss right at the start of the supply chain.
Ouch. Can we fix that? Because losing nearly half your energy just to change the state of the fuel seems like a potential deal breaker.
The report says, yes, we can. The current process is based on decades-old technology. There are new conceptual designs for liquefiers using things like magnetic refrigeration that could theoretically cut that energy cost in half.
So get it down to maybe 15 or 20% loss.
That's the target. But we aren't there yet. And there's another bottleneck right alongside the energy cost.
Yeah.
Simple capacity.
Right. The report mentioned that the total global production capacity for liquid hydrogen is only about 350 tons per day.
Which sounds like a lot, until you realize that a single large airport or a major trucking fleet could chew through a significant fraction of that.
We're not at the scale we need.
Not even close. We need to be building single plants that can produce 100 tons per day or more. Right now, the biggest ones in the world are doing maybe 30. So we need to build bigger, and we need to build them to be far more efficient. We need to scale up massive, powerful, efficient refrigerators, essentially.
So we have made the liquid, we've paid the enormous energy tax, now we have to put it in a tank and, crucially, keep it cold. This brings us to part 3 of the report, storage. And the analogy they use throughout this section is perfect. The thermos.
It is a perfect analogy, because if you want to keep your coffee hot or your liquid hydrogen cold, the principle is the same. You need a double-wall container with a vacuum in between to stop heat transfer.
But the report makes a really critical distinction right away between space tanks and Earth tanks. They're not the same thing at all.
This is a key point. In space exploration, think about the Space Shuttle's Big Orange tank or the massive Saturn V rockets. They used what were essentially single-wall tanks with a layer of spray-on foam insulation.
Just foam, like a high-tech beer cooler.
Essentially, yes. And the reason they could get away with that is that they only needed to hold that super cold fuel for a few hours.
Right. They fill it up on the Launchpad, they go through the countdown.
They blast off, and the tank is empty in minutes. They didn't really care if it boiled off a little bit while it was sitting there for a few hours. It was an acceptable loss.
But a truck driver might need that fuel to sit in their tank for days or even a week. If you park your truck on a Friday, you absolutely expect there to be fuel in it on Monday morning.
Exactly. For mobility applications, for trucks, planes, and ships, foam isn't nearly good enough. You need something much more robust. You need double-wall, vacuum-jacketed doors.
Okay, that's a mouthful.
It is, but it's just a technical term for a thermos. You have a strong inner tank that holds the cold liquid. You have a sturdy outer tank that you see on the outside. And in between those two walls, you have a hard vacuum.
To stop heat from conducting or convecting across the gap?
Precisely. But even with a perfect vacuum, heat can still radiate across. So inside that vacuum gap, you need insulation. And the report lists a whole hierarchy of different materials.
It gets really nerdy here, which I love.
It does. At the basic level, you have things like perlite, which is a kind of volcanic glass powder. It's cheap and it works okay. You have glass bubbles. But at the top of the performance food chain, you have aerogels and something called multilayer insulation, or MLI.
What's MLI?
It's basically like wrapping the inner tank in dozens of layers of super thin, shiny aluminum foil separated by spacers. Each layer reflects a little bit of the incoming heat radiation. It's incredibly effective.
It also sounds incredibly expensive and difficult to install.
It is, but if you want to stop the #1 enemy of liquid hydrogen storage, you need it. And that enemy is boil-off.
Let's talk about boil-off. That sounds like a constant ticking clock.
It is the nemesis of liquid hydrogen. Heat is always trying to get in. No matter how good your thermos is, some amount of heat will eventually leak through the walls, through the pipes, through the support structures.
And when that heat hits the negative 253-degree liquid,
it makes it boil. The liquid warms up and turns back into gas. Now, if you don't do anything about that gas, the pressure inside the tank will build and build and build until the tank fails catastrophically. It'll explode. So you have to vent that gas.
So your fuel is literally evaporating into thin air while your truck is just parked.
If you rely on what the report calls passive management, which is just insulation, then yes, a certain percentage of your fuel will boil off every single day.
That's lost money. And it's an emission, even if it's just hydrogen.
It is, which is why the industry is moving toward active management. This means putting small cryocoolers or refrigeration units on the vehicle itself.
A mini fridge for your fuel tank.
That's basically it. A device that can grab that incoming heat and actively pump it back out, keeping the liquid stable. Another technique is called densification, which is where you subcool the liquid even further below its boiling point so it can absorb more heat before it even starts to boil.
The report also mentions that we are moving away from traditional materials for the tanks themselves, away from steel.
Right. Stainless steel is a traditional choice. It's strong, and it handles the extreme cold very well without becoming brittle. But it is very, very heavy.
And if you're building an airplane, heavy is the enemy.
Heavy is the enemy. Every kilogram of tank is a kilogram of passenger or cargo you can't carry. So companies like Airbus are pioneering the use of composite tanks, things like carbon fiber blends that are both incredibly strong and incredibly light.
But can carbon fiber handle that kind of cold? I think of it as being somewhat brittle.
That's the engineering challenge, developing composite materials and resin systems that can handle the massive thermal stress of going from room temperature down to 253 degrees without developing microcracks. It's a huge area of research.
There was one other storage method mentioned in the report that seemed like a sort of hybrid approach, cryo-compressed storage.
This is a fascinating technology that tries to get the best of both worlds. Instead of just having cold liquid at low pressure, you have very cold hydrogen at a higher pressure.
So it's cold A and D compressed.
Yes. You cool it down until it's a liquid, but then you allow the pressure to build up, putting it into what's called a supercritical state. It's not quite a liquid and not quite a gas.
What is the benefit there? Why do that?
Higher density. You can pack even more hydrogen molecules into the same volume than you can with standard liquid hydrogen. It also helps manage the boil-off problem because the tank is designed to handle that higher pressure.
And the report highlights a great real-world example of this from Daimler Truck.
Yes, they've developed a fueling process they call SLH2 for subcooled liquid hydrogen. And with it, they can pump 80 kilograms of fuel into a truck in about 15 minutes, and they do it without needing a return vent line for the gas.
That's a big deal. That starts to sound like the speed and convenience of filling up with diesel.
That's the goal. That's the holy grail of operations. Parity with the fossil fuel experience. If it takes a driver an hour to refuel a truck, they won't accept it. The economics of the whole industry falls apart.
So we have the fuel in the tank. Now we have to actually use it. Part 4 of the report covers operations and safety. And I have to be honest, reading through some of this, it sounds genuinely terrifying.
It demands respect.
Yeah.
There's no doubt about it. You are dealing with physics at its absolute extremes.
One of the first operational challenges they mention is something called chill down. You can't just open the tap and pour liquid hydrogen into a warm pipe, can you?
Absolutely not. If you pour a negative 253 degrees Celsius liquid into a pipe that's at room temperature, the liquid will hit that warm metal and instantly, violently flash into gas.
A flash boil.
A massive one. The liquid expands nearly 800 times in volume almost instantaneously. That creates a huge pressure spike, a shock wave, that can literally blow pipes and valves apart. It's called a rapid phase transition event.
So what do you do? How do you fuel a vehicle?
You have to do it slowly and carefully. First, you have to flow very cold hydrogen gas through the pipes and the tank to gradually cool all the metal down. Only when the entire system is chilled to cryogenic temperatures can you begin to introduce the liquid.
So it adds time and complexity to every single fueling event. You can't just plug it in and walk away.
Correct. It requires automated, carefully controlled procedures.
And then there's this other phenomenon they describe called ullage collapse.
This is a really subtle one. This is a danger that keeps cryogenic engineers up at night.
Okay, explain it. Ullage is the gas space at the top of the tank, right?
Right. Imagine your tank is half full. You've got liquid at the bottom and hydrogen gas or ullage at the top. Now, if the vehicle hits a big bump or goes around a sharp corner, that super cold liquid can slosh up and spray into the warmer gas above it.
And it would cool that gas down really, really fast.
Instantly. And when gas gets cold, its pressure drops. So the cold liquid spray causes the gas to condense and the pressure in the entire tank can drop like a rock. A near-instant vacuum can be created.
And what's the danger there?
Two things. One, if the pressure drops too low, the external atmospheric pressure could actually be strong enough to crush the tank and make it implode. Two, the fuel pumps that feed the engine or fuel cell need a certain amount of positive pressure to work. If the pressure collapses, the pump cavitates, and the engine starves of fuel.
So how do you prevent that? You need baffles inside the tank.
You need baffles to prevent the sloshing, absolutely. And you need active pressure control systems that can inject warm gas back into the ullage if the pressure starts to drop too quickly. It proves that the tank isn't just a hollow metal can. It's a complex, actively managed fluid system.
Let's pivot to the broader topic of safety, because this is where public perception really comes into play. People have a lot of fears about hydrogen, some of them justified, some may be based on old black and white newsreels of the Hindenburg.
The Hindenburg looms large in the public imagination for sure.
And the report does a good job of busting a few myths, but it also highlights some very real and maybe counterintuitive dangers.
It does. Let's start with the fire itself. A hydrogen fire is very, very strange. The report points out that a pure hydrogen flame emits almost no radiant heat.
Wait, what does that mean? A fire that isn't hot?
Oh, it's incredibly hot if you touch it. The flame itself is thousands of degrees.
Hmm.
But if you stand next to a normal campfire, you can feel the heat on your face from several feet away. Right? That's radiant heat.
Sure.
Hydrogen flames don't do that very much. You could be standing a few feet away from a large hydrogen fire and not feel any heat. You wouldn't realize it was burning until you accidentally stepped into it.
And it's also invisible.
In broad daylight, yes, it's almost completely invisible. You might see a little heat shimmer in the air, but you won't see a flame. At night, it burns with a pale blue color.
That is terrifying. An invisible fire that you can't feel.
It's a serious hazard. The report is clear that any facility handling liquid hydrogen needs specialized infrared sensors or UV flame detectors. You need cameras to see a fire. You cannot rely on human eyes or senses.
But there is a bit of good news when it comes to spills, right? Something that makes it safer than gasoline in some scenarios.
Yes, and it's a huge advantage. Buoyancy. Hydrogen is the lightest element in the universe. It is incredibly light. If you have a leak, the gas rises at a speed of 20 meters per second.
That is
It's
fast.
like a reverse rocket. So think about a car crash. If you spill gasoline, it pools on the ground. The heavy vapors spread out and create a lingering fire hazard that's hard to get rid of.
Right.
If you have a liquid hydrogen spill, it flashes to gas and shoots straight up into the atmosphere and dissipates very, very quickly. So in an open-air environment, the danger can actually clear out much faster than with a conventional fuel spill.
There was one other danger mentioned that I had never even considered. Air condensing.
This is a really weird side effect of working with these extreme temperatures. The pipes and valves carrying the liquid hydrogen are at negative 253 degrees Celsius. The air around us is made of nitrogen and oxygen, and their boiling points are much higher than that.
So the pipes are so cold they can freeze the air.
They can liquefy it. The air that touches the cold pipe will condense into liquid air, which will drip off the pipes.
Okay, so you have little puddles of liquid air. What's the problem?
The problem is that liquid nitrogen evaporates slightly faster than liquid oxygen. So what's left behind is a puddle of liquid that is highly oxygen enriched. And liquid oxygen is an incredibly powerful oxidizer. If that drips onto something flammable like asphalt or an oily rag or even just pavement, it creates a massive explosive flammability hazard.
Wow. So you have to insulate the pipes not just to keep the hydrogen cold inside, but to keep the air from freezing on the outside.
Exactly. It's a dual-purpose safety measure. And of course, the most immediate danger to any human working with this stuff isn't even the fire. It's the frostbite, the extreme cold. Direct contact with liquid hydrogen or any uninsulated metal at that temperature will cause severe, instantaneous frostbite. It will freeze flesh solid. It's a serious industrial hazard that requires extensive training and specialized personal protective equipment. You cannot handle this stuff with your bare hands. Okay, moving on to part 5. Economics, strategy, and what the report calls the valley of death. This is where the rubber really meets the road. We can build it, but can we make money doing it?
Right now, it is very, very tough. And that valley of death is the treacherous gap between having a cool prototype that works in a lab and having a commercially viable product that people will actually buy and that can compete in the market.
The U.S. Department of Energy has a very ambitious goal for this, though. They call it the hydrogen shot.
The 111 goal. It's a great, simple target. They want to get the cost of clean green hydrogen down to $1 for 1 kilogram in 1 decade.
$1 per kilogram. Where are we now, roughly?
Oh, a long way from there. Depending on how you make it and where you are, you're looking at anywhere from $5 to $12 per kilogram or even more by the time it gets to the pump.
So we need a massive cost reduction. We need to cut the price by nearly 90% in some cases to be able to compete with cheap diesel fuel.
A massive reduction. It requires breakthroughs in electrolyzer efficiency, manufacturing scale, and the cost of renewable electricity. And beyond the cost of the fuel itself, there's the infrastructure gap, the classic chicken and egg problem.
Precisely. You can't sell a fleet of hydrogen trucks to a company if there are no fueling stations on their routes. And you can't get anyone to invest hundreds of millions of dollars to build a fueling station if there are no trucks to buy the fuel.
So who goes first?
It's a real standoff. And the report highlights a business practice that makes it even harder. The take-or-pay model that suppliers are using.
Explain what that is.
Because those liquefaction plants we talked about are so expensive and energy-intensive, you can't just turn them on or off like a light switch. They need to run continuously. So the suppliers force their early customers to sign these really restrictive contracts.
They guarantee they'll buy a certain amount.
They have to guarantee they will buy a fixed amount of liquid hydrogen every month, whether they actually use it or not. If their trucks are down for maintenance, too bad. You still have to pay.
That is a huge financial risk for a small trucking company that's just trying to test out a few new vehicles.
It's a massive barrier to entry. It really favors the giant, deep-pocketed players who can afford to take that kind of financial risk.
Let's zoom out and look at the global map for a second. The report breaks down some of the different regional strategies we're seeing.
It's a global race, and everyone's taking a slightly different approach. You have a country like Australia, which has, well, it has a lot of empty land and a lot of sunshine and wind.
A renewable energy superpower in the making.
Potentially. So their strategy isn't just to make hydrogen for themselves, but to become a major energy exporter, make massive quantities of green hydrogen, and ship it to countries that need it.
And the report mentioned a major milestone in that effort. The first ever international shipment of liquid hydrogen by sea.
Yes, this was a huge deal. In February 2022, a specially built ship called the Suzo Frontier, which means Hydrogen Frontier, sailed from Australia to Japan carrying a cargo of liquid hydrogen.
So it proved the concept.
It proved you can put this stuff on a boat, cross an ocean, and deliver it safely. And Japan is the perfect example of the hungry customer in this model. They're an energy-poor nation. They don't have the land for massive solar or wind farms, so their strategy is to import clean energy.
What about China? The report mentions them specifically.
The report calls them the largest producer and consumer of hydrogen in the world already, mostly gray hydrogen for industrial uses, but they have a very aggressive national strategy to build out green hydrogen infrastructure. When Beijing decides to do something, they tend to move very, very fast.
And the U.S., what's the American approach?
The U.S. is focusing heavily on the hydrogen hubs concept. Yeah. The bipartisan infrastructure law allocated about $7 billion to fund several of these hubs across the country.
And the idea is to create these dense regional clusters.
Exactly, to create clusters where the production of hydrogen and the use of hydrogen happen in the same geographic area. You put the electrolyzer next to the port, which has hydrogen-powered tugboats and trucks. You minimize the need for long-distance transportation, which is one of the biggest costs.
One thing the report really stresses, regardless of region, is the urgent need for standards.
They call it the USB port problem.
It's a perfect analogy. Right now, there is no standard fueling nozzle for liquid hydrogen.
None. Every manufacturer, Daimler, Hyundai, Nikola, they're all developing their own proprietary connectors.
Imagine if you pulled up to a gas station and the nozzle didn't fit your car because you bought a Ford instead of a Chevy. It would be chaos.
That is exactly where we are today with liquid hydrogen. We desperately need industry and governments to agree on universal standards for the nozzles, for the hoses, for communication protocols, for safety systems. Without that standardization, you can't build a public network.
Let's look to the future. The final part of the report lays out a possible timeline for how this might all unfold. What can we expect in the near term, say, the next 0 to 5 years?
More demonstrations, a lot more pilot projects. You'll see more hydrogen buses on city routes, more tests of hydrogen-powered trains. But one big shift the report predicts is the rise of hydrogen combustion engines.
So not fuel cells, actually burning hydrogen in a piston engine, like a diesel engine.
Yes. Companies like Toyota and Cummins are investing heavily in this. It's less efficient than a fuel cell, so you don't get as much range. But the engine itself is much cheaper to build, and it's based on technology that we've been perfecting for over a century. It might be a crucial bridge technology to get us started.
And what about the medium term, say 5 to 10 years from now?
This is where aviation starts to get really interesting. The report suggests we will start to see the first regional aircraft, we're talking smaller, 50 to 100-seat commuter planes, actually flying commercial routes on liquid hydrogen.
Wow. And to support that, we'll see the development of microliquefaction at airports.
Exactly. Instead of trucking the liquid hydrogen in from a giant central plant, you'll have smaller modular liquefaction units right at the airport. You make the fuel right there at the tarmac.
You eliminate the most expensive part of the supply chain, the delivery truck.
That's the idea.
And then long term, 10 years and beyond.
This is where you get to the big prizes. Large, long-range aircraft. The jumbo jets. You'll see hydrogen becoming a truly fungible commodity traded on the global market, just like a barrel of oil is today. And hopefully, we'll see it reach cost parity with fossil fuels, especially if carbon pricing or carbon taxes come into play.
It's a massive, decades-long roadmap. So to wrap this incredible deep dive up, let's try to summarize where we are. We started this journey with the Saturn V rocket, the legacy of the space program.
And we've brought it all the way down to the delivery truck and the commuter airplane. We've learned that liquid hydrogen is incredibly energy-dense by weight, it's potent, and it's fundamentally clean at the point of use. But it demands our respect.
The physics of cryogenics, the massive energy cost of liquefaction, the constant battle against boil-off, these are not small engineering hurdles.
They are real, they are difficult, and they will be expensive to overcome. But the potential payoff, a decarbonized heavy transport sector, is almost immeasurably large.
Absolutely. Before we sign off, I want to leave our listeners with one final provocative thought that was tucked away in the report. It briefly mentioned island nations and remote regions.
This really stuck with me too. If you're a remote community or an island nation, you are probably 100% reliant on diesel shipments today. If the ship doesn't come, your power plant shuts down. The lights go out.
You're at the mercy of a very long and fragile supply chain, but with hydrogen.
Think about it. If you have sun or wind or wave power, you can make your own electricity. You can use that electricity to split water, which an island have plenty of, to make your own green hydrogen.
You can store that hydrogen in tanks for when the sun isn't shining or the wind isn't blowing.
And use it to run your power plant at night. You can use it to fuel your island's cars and boats. And the only byproduct from the fuel cells is pure, fresh water, which can also be a scarce resource in some of those places.
A completely closed loop, total energy independence, bypassing the entire global fossil fuel grid.
It's an incredibly powerful idea. Hydrogen doesn't just have the potential to clean up the air in our big cities. It could fundamentally change the geopolitics of energy and empower remote communities in a way that has never been possible before.
That is definitely something to think about. Look for the invisible flame of progress, everyone, and stay curious.
See you next time.